Hospital monitors are blaring. The patient's potassium levels spike rapidly, while calcium fractions drop towards zero. They are seconds away from sudden cardiac arrest. The medical team is looking for a rare poison or a catastrophic genetic failure. But the culprit dismantling this patient's physiology is a massive overdose of a household element, fluoride. To understand how this chemical can trigger such a collapse, we must look back at the evolutionary record. Early marine life built skeletons out of calcium carbonate, a material suited for a stable aquatic existence. But as vertebrates moved onto land, they encountered a much harsher environment. Survival required tougher materials. Early land animals began repurposing trace amounts of environmental fluoride from the soil and water to construct harder, acid-resistant surface barriers. Terrestrial biology integrated this reactive chemical agent into the structural foundation of the human machine. Fluoride is a highly electronegative monovalent anion. Carrying a single negative charge, this tiny particle aggressively seeks out positive charges, acting as a microscopic magnet for calcium. Inside the enamel's calcium phosphate matrix, the fluoride ion systematically penetrates the surface, ejects standard hydroxyl molecules, and replaces them. This creates shorter, stronger chemical bonds. It lowers the crystal array's local entropy, pulling a loose arrangement into a tightly packed, rigid lattice. This substitution shifts the thermodynamic threshold of the skeleton. Standard enamel dissolves at a pH of 5.5, but this new matrix, called fluoroapatite, resists dissolution until the pH drops to 4.5. Because of its reactive nature, the human body locks 99% of its fluoride inside the mineralized skeletal vault. In a healthy state, blood serum concentrations remain extremely low, but the fluoride that does circulate acts as an antimicrobial. As a charged ion, it cannot cross a bacterial cell wall. It simply bounces off. To get inside, it utilizes the acidic environment created by the bacteria themselves. The fluoride ion binds to a free proton in the plaque matrix to form hydrogen fluoride, or HF. Because HF is uncharged and lipid-soluble, it passes through the bacterial cell wall undetected. Once inside the alkaline cytoplasm, the molecule splits apart, releasing a charged fluoride ion that deactivates the enolase enzyme and starves the bacteria of energy. Managing this balance requires a master controller. The renal system must constantly flush excess fluoride from the blood to prevent it from attacking our own tissue. The kidneys handle this through a pH trapping loop. In acidic urine, fluoride forms HF and diffuses back into the blood. In alkaline urine, it remains a charged ion, trapped in the fluid until it is flushed out of the body. Human survival depends on this constant acid-base negotiation, deploying enough fluoride to assassinate bacteria without retaining enough to destroy our own cells. When that negotiation fails, as in a massive toxic ingestion, the homeostatic matrix is breached. In the bloodstream, free fluoride ions aggressively bind to circulating calcium. This causes profound hypocalcemia, leading to painful muscle tetany and seizures as the nervous system loses its stability. Simultaneously, the fluoride penetrates human cells and deactivates human enolase. This stops glycolysis, the engine of cellular energy production. Cells rely on this energy to run mechanical pumps, keeping potassium inside. When they fail, potassium floods the blood, short-circuiting the heart's rhythm. While acute poisoning is rapid, chronic overload is a slow structural shift. In industrial settings or regions with naturally high fluoride, continuous exposure creates a different pathology. This chronic accumulation leads to skeletal fluorosis. Unchecked bone stimulation causes the spinal ligaments to calcify, eventually fusing the spine into a rigid, inelastic cage. The same trace element that builds our armor can, in excess, turn the body's flexibility into a fused cage or trigger an immediate metabolic collapse. Responding to a fluoride crisis requires immediate intervention. Doctors use calcium chloride or milk to precipitate the fluoride into solid stones in the gut, while preparing for emergent hemodialysis to scrub the blood. To guide that treatment, the clinical laboratory uses an ion-selective electrode to measure the fluoride invasion. Because fluoride clamps onto metals like calcium and magnesium in the blood, it is often hidden from the analyzer. The lab must add a buffer called TISAB, which contains a chelating agent that forcibly detaches the fluoride so it can be detected. but the measurement is vulnerable to a simple pre-analytical pitfall. Fluoride reacts with silicate networks, meaning a sample collected in a standard glass tube will leach silicate fluoride and destroy the sample's integrity. An even more significant error occurs when a sample is drawn into a gray top tube, a container preloaded by the manufacturer with massive amounts of industrial sodium fluoride. The analyzer detects the tube's own chemical additive, spitting out an off-the-charts panic value. This tricks the medical team into responding to a toxicity that doesn't exist. Harnessing fluoride requires an alignment between human physiology and laboratory architecture. From our teeth's mineral density to test tube additives, our reality is dictated by the physical chemistry of a single trace element.